Now, antiderivatives. Basically, what we've been doing is we've been going forward. We have a function f, and we're going to find the derivative f primed. But what if they give you a function and you want to find the function whose derivative is f primed? So rather than taking the derivative, you want to go backwards. Find the antiderivative. Well, so that's what we're going to do. That's at least what we're going to introduce in this section, right? The idea, and we're going to look at pretty much simple antiderivatives that you can kind of figure out because you know the table of derivatives. So it's just from the table of derivatives, kind of just go the other way on those simple antiderivatives. For example, if I'm given, and by the way, notationally what we'll be using, if they give you little f, for example, I'll take little f of x equals x squared. If this is now my derivative, what function do I have to take the derivative of to get that? And we're going to use the big F for the antiderivative. And so you know that if I take the derivative of x cubed, right, I'm going to get 3x squared, right? So the derivative of x cubed is 3x squared, just power rule, right? Now, but here I don't have a 3, right? However, I know I can also multiply by constants, so just kind of mentally figuring it out, the derivative of 1/3 3x cubed is going to be 1/3 times 3x squared. The 3's are going to cancel out, and I get x squared, right? So just sort of kind of working that out. So this is almost what I need. But if I think about what happens with the power rule, I know that I have to take that down, and that guy's going to go down. So if I multiply by the right constant, then I can see here from what I've done, an antiderivative of f of x equals x squared is big f of x equals 1/3 x cubed. Okay? The question now is, all right, why did I write an antiderivative? Well, remember that taking the derivative of a constant is 0. So another function that would give me this as a derivative, I could do f of x equals 1/3 x cubed plus 1, right? The derivative of this is also little f. I can put whatever I want for my constant. I'm still going to get this as my derivative because the derivative kills the constant. So, and you can show that with the mean value theorem, by the way. You can show that if I have any two functions, big F and big G, both of whose derivative is little f, then they're two different functions, but they differ by a constant. So that's very straightforward to show. In any case, so what I really want to say about that is that then what we do is we can talk about an antiderivative, and you could pick any one of these you wanted. But if we want the most general antiderivative, then what we do is we use a plus c, right? You just would be, so I would write f of x equals 1/3 x cubed, and the convention is to use an uppercase c for your constant. All right, and I think on WebAssign it will specify use an uppercase c for your arbitrary constant, and that's what we call this. We call this the arbitrary constant because any number there is going to give me another antiderivative of my original function. However, it really doesn't matter what that constant, like it doesn't matter what that constant is. We'll see some problems where they give us more information and then we can find what that constant is for that specific problem. Specifically like some standard sort of applications from chemistry where you were given the velocity and you want to find the position. Stuff like that. So we'll do some examples like that later. But in general, you were just expected then to put a plus c there for your arbitrary constant. So, let's do a couple quick ones. Find the general antiderivative of, let's see, let's do these 3. All right, that third one has a little bit of more work to do. But so for this first one, we know that the derivative of sine is cosine, right? You just know that from your derivative rules. So the antiderivative of cosine is sine. I'm going to call them F1, F2, F3. So this is big F1. Big F2, this is very similar, right? We just did x squared, so this is x to the 4th, right? If I have x to the 5th, I'm going to take the derivative of x to the 5th, and we have 5x to the 4th. So I have extra 5, get rid of it by throwing a constant in front. Easy. All right, this third one we got to think about for a minute. Okay, because find the most general antiderivative. So we know that the derivative of natural log is 1 over x, right? Sure. So you know that it's got to be something like that, right? But if I just write f of x equals natural log of x, okay, this domain here is only positive stuff, right? Because I can't take natural log of a negative number. But this here, I could also have negative values. So I'm not sure if we talked about this when we learned about logarithms or not, which is why I want to talk about it right now. Let's take a little bit of not really a detour, but let's define y to be natural log of absolute value of x. All right? What is dy dx? Okay? So now natural log of absolute value of x, this now is defined everywhere except 0, right? So if I look at what this is, I'm going to write it over here. Y is natural log of absolute value of x. It is natural log of x for x positive and natural log of negative x for x negative. So now if I take the derivative, the first one we know, right? It's just 1 over x. Now what about this one? Also, I can chain rule this, right? So this would be 1 over negative x times the derivative of negative x, which is negative 1, right? So I'm just going to keep writing. Negative x times negative 1. So eventually we also get 1 over x. Okay? So this is a little bit of a special case because of the fact that we have natural log and we have to take care of making sure that our natural log of our thing is actually defined. But the most general antiderivative of 1 over x is actually going to be natural log of absolute value of x. Okay, so this, my big F3 here, is going to be natural log of absolute value of x plus c. There's a table of anti-differentiation formulas that I put up in our module, which is basically just a regular table of derivatives, but put on backwards. But you'll see it does have the absolute value of x in that one.